Receive.
Recording is on.
Hello, are people on?
I'm on. Steve Ritz.
William Oberline here. You have 10 people collected, Mike.
Federico, I think you're speaking, but we can't really hear you. We're hearing, not sure if the sound is going through properly. We're hearing.
I can hear you now, but I have some significant connection issues right now. I'm trying to fix it by connecting
Now I
on my
can hear
phone.
you fine.
Okay. So I turned off my video, but I think that we're still recording everybody else. Let's see who we have. Oh, good people. We are still waiting for guests. That's a mistake.
There's a lot of background noise which seems to be coming from Federica, like a lot, like as if there were a lot of people talking in the room or something.
Let me then mute here and see if I can connect on my phone. I'm gonna leave this on. For recording. Hello, can you hear me?
Yes.
Bit of an echo.
Is it better with the background noise now that I muted my computer?
Yes.
Much better, much better. Thank you.
All right. Sorry about that. See if we have already not yet.
All right, I'm online. Should I just jump right in, or is there a business to take up beforehand?
No, sorry. No, we can jump right in. I was just trying to get a sense of who's here. I think most science collaborations are here. So, yeah, thank you for agreeing to talk to us, Jim. So today is the talk about the DM. Take it away.
Alrighty. Please jump in if you have any questions. Note that I will not be able to see you waving at me furiously in the video because when I'm presenting, that's be everything I see. So you'll just have to speak up, and hopefully we can deal with the telecom managing that.
And if
I
you
hope
leave a
everyone can
message on the chat, sorry, if you leave a message on the chat, I can try to moderate and interrupt with questions if they seem worth interrupting. Speaking of which, Phil has uploaded a link for the live notes on the chat. So if you want to contribute to that, please feel free. Although I think Phil will lead the note taking.
I've forgotten there's a link for the slides.
Yeah, there's a link for the slides in the email. If someone else could paste that in, please.
Okay, thank you.
Yes, I'll do that. And I'll upload it on slide.
Okay. Hopefully everyone can see my slides through BlueJeans as well. All right, so first for some context, this is the first of 6 talks on LSST data products that are planned over the next few months. This is the pipelines and data products overview. Then there'll be Robert Lupton talking about the photometric data products. I don't think we know yet who's going to be talking about astrometry. Eric Bellin will talk about the alert stream. Blended sources, we have a few candidates. I'm one of them, but we're not quite sure who's going to talk about blended sources yet. And then Mario will finish with talking about the moving object pipelines. And before I dive in further, I wanted to provide a little bit of a glossary. So I don't expect you to remember all of this up front, but hopefully this will at least make some acronyms and things familiar and maybe say something about how we're moving in terms of nomenclature, because we haven't always been very consistent about this. So first off, source and object. This is an LSST, I think, peculiarity, but people who've been with LSST are hopefully by now familiar with this. A source means measurements at a single epoch. An object means measurements utilizing multiple epochs, typically all of them. That's backwards from how some people think, but I think LSST is pretty locked into those terms right now. A PVI is the latest and best way to refer to a processed visit image. In other words, our best estimates for the image of corresponding to a single visit. Now, that's 2 snaps. We've in the past called these CalEx, so that's still what the pipeline calls them, but we'll probably switch that eventually. You may have also seen them referred to as calibrated exposures. DIA is a prefix we use for lots of data products, and that means difference imaging analysis. So this is data products that are derived from difference images. MOPS is the moving object processing system. It's how we create and constrain solar system objects. AP means alert production. That's both the team at University of Washington Data Management who works on that. It also means, in that sense, more than just the stuff that produces the alerts. It's everything that happens on sort of that daily cadence, daily, nightly, whatever you want to call it. We've taken more recently to start calling these the prompt data products. And so I think we'll try to move towards that nomenclature. You'll still see them referred to as nightly and as alert, even things that are not alerts. One thing we're not trying to call these anymore is level 1. The level 1, level 2, level 3 nomenclature was very confusing for lots of people, especially because it was often used to describe two completely different things. And so we're trying to move away from that. DRP is the analogy for the Princeton team of data management that works on the pipelines for the data release production. This is mostly, or more or less annual or yearly, and was some context previously called level 2. User-generated is the new term for what used to be called level 3. Any quick questions about that?
Yes, Jim, I have a question actually. The alert production includes both the things that come out 60 seconds after the image as well as things that come out on a 24-hour timeline. Is there a different nomenclature for the two products?
There isn't really any nomenclature to distinguish those, or to the extent that there is, it's very confusing. So when I refer to alert production or prompt or nightly, I mean both of those things, the 60-second products and the 24-hour products.
Mm-hmm. Thank you.
Sure. All right, so the way I'm going to go through this is a little bit unusual. I think most of our documents tend to start with the level 1, or what used to be the level 1, the prompt, the alert production stuff, and then move to data release. I'm going to start with data release and then talk about prompt sort of as a special case of that. I think that's actually an easier way to understand everything. So a data release involves all of the data sets that we will produce, all the data products. It's what you would use for static sky science, and it's what you would use for most time domain science. I think there's a lot of misconception about the idea that you would use the prompt processing for time domain science and you would use the data releases only for static sky. Data release is actually what you would use for a lot of time domain as well, and we'll see why as we get into this. The prompt is I would think of it as a pre-release version of the single epic data products from the data release. And it also involves alerts, which we of course don't do any alerts in the data release processing. Prompt is I think mostly for transient and time domain science that requires fast follow-up. Some things where you can't wait a year, either because you need to point a big telescope at it, or because you just want to get your science out fast. So here's a flow chart that's sort of a big overview of data release processing. I'm going to show you a lot of flow charts of this type, and I'm not going to step through all of them in detail. This one is the most zoomed out one, and we will eventually step through all these things in detail. But for the rest, I think I'm happy to follow up later. But if you have questions about exactly how we do something, this is probably not the presentation to try to talk about that with. So just broadly speaking, we start with raw images, calibration images, reference catalogs. We calibrate those individual images to the best of our ability. Sometimes that involves looking at multiple images at once. That produces sources, and it produces those PVI images. We then co-add those images and difference them. These are all image processing sort of operations. And in addition to producing co-adds and difference images and DIA sources, the sources derived from difference images, it also produces better masks and better sky backgrounds. So there's actually an opportunity to iterate back to the image characterization steps there. And we're not quite sure how we'll resolve that circular dependency there. It's probably sort of one step of iteration rather than n steps. After we've done the co-addition and the difference imaging, we'll do co-add processing, in which we start to produce objects and we produce DIA objects, and we then move on to multi-epic object characterization, where we improve our measurements of those objects and we do force photometry. So we'll start by zooming in on this image characterization and calibration step. So this is the blow-up, a zoomed-in version of just that step. You can see we start from the same inputs. They're all images, the calibration images, the reference catalogs. And there are three big pipeline steps. There's Bootstrap, what I'm calling Bootstrap, Joint Cal, and MCAR for image characterization. And the idea is that we start by sort of bootstrapping our best estimates of all the things about the image, the PSF, the WCS, the photometric calibration, et cetera. And that makes preliminary versions of a lot of stuff. And then we run Joint Cal. And Joint Cal is an operation in which we try to solve for a lot of those things simultaneously over the overlapping images. And as many of you know, that's a much better way to constrain your photometric calibration and your astrometric calibration, et cetera. So we improve all those things, and then we put the improved versions all into image characterization. That's when we make our final version of the PVIs and the sources. and possibly we'll take some stuff from the next step, as I'd said before. So what's a PVI? A PVI is one image for every visit and sensor combination. Even though we say processed visit image, there really is one image for every sensor. That includes, in addition to the image, photometric calibration, which is wavelength dependent, the astrometric calibration, also called a WCS. This includes the distortions. It's not a simple fits WCS. We're defining this to not be wavelength dependent. And that works because we're defining the point spread function in a way that is wavelength dependent, and it might include shifts. So there's sort of a degeneracy between the WCS and the PSF. And the way we've resolved that degeneracy is to say that the point spread function have shifts, but it is wavelength dependent, while the WCS is not wavelength dependent. That just simplifies some of the processing. It also includes a background model, which is not wavelength dependent, but it is solved for using flats that are appropriate for the spectrum of the sky. And as Robert will talk discuss in the next talk, we use different flats for different objects effectively. There's also a variance plane and a set of masks to go with every PVI as well. Sources. So sources is a table of detections and measurements that are derived from PVIs, and sources are derived from only one PVI, the single epic image in which the source was measured and detected. So this includes centroids, it includes aperture and PSF photometry, it includes adaptive moment shapes, where you adaptively match a Gaussian to the size of the object and then use that as a weight function to measure the second moments of the object. It'll also include some simple morphological star-galaxy separation. It won't be our best star-galaxy separation. I think sources are probably most valuable for diagnostic purposes, and I think that's a bit confusing. There's a long history of doing science with things that are basically sources. All the SDSS survey ever had were sources. So if you're used to using SDSS data or other surveys like it, it can be a bit difficult to wrap your head around the idea that you should be using something other than sources to get the optimal measurements. In particular, if you're interested in the static sky or in stellar astrometry, you probably want to be using measurements from the object table instead. If you're interested in variables, you probably want to use the force sources instead. You'll get better light curves from the force photometry. And for transient or solar system objects, you probably want to use DSOurce or the SS object, solar system object tables instead. Sources can measure all of these things, they just don't measure them as well, largely because we're not enforcing any kind of consistency between the different epochs. But they are, of course, very important for diagnostic purposes, and it's important to have them in the database, so you can see if your higher quality measurements from a more complex measurement in, say, object agree with what you see in sources. So looking back at the big zoomed out picture, we're next going to dive into coaddition and difference imaging. And here's the zoomed in version of that diagram. So you can see we start from the outputs of image characterization and calibration, or at least the PVIs. We do a lot of resampling and messing with the PSF that I'm not going to go into detail on right now. We do some better artifact detection and background matching to improve the masks and the backgrounds. But ultimately, we create three different kinds of coads: direct coads, matched coads, that's PSF matched coads, and detection coads. I'm not going to talk too much about detection coads. Suffice to say that they are a certain kind of coad that is optimized for detection, and I'm not going to use them for anything else. Once we have those, we'll take the matched coads and the PVIs and we'll subtract the difference imaging. That produces difference images, and then we'll do difference image processing, which makes those DIA sources. So coads, there's lots of different flavors of coads. The first one, and the simplest, is what I call direct coads. In this case, we combine the warps, the images that the single epic image that we've resampled, warped onto the same coordinate system. We just combine those with no special treatment of the PSFs. That means we're adding images with different PSFs, and you have to be very careful doing that. And you can't use things like medians, but if you use a linear estimator for the pixels of the coad, this is mathematically very similar to just taking longer. If you weighted by the exposure time instead of by the variance in every image, it would be exactly equivalent to taking longer exposures, modulo tiny things like read noise. This is what we plan to use for deblending and most measurements. It's where we expect to have sort of the best image quality coads, minimizes the correlated noise, and you can determine an effective coad PSF by combining the PSF models of the individual epochs with the same weights. I realize the way I wrote that in the slides just doesn't make any sense. So I'll update the slides after the talk, but I hope that makes sense. This is the way we're building coads right now for the HSC pipeline processing. Matched coads. So matched means PSF matched. And in this case, we convolve each of those warps with the difference kernel to match the PSF of that epoch to some constant PSF. And therefore, when we add the images, they all have the same PSF. That's useful for artifact detection and masking because you don't expect to see any differences between epochs, except for the case of actual transients and variables or garbage. And it makes it a good way to find garbage. We also will use these as the templates for difference imaging, not because we'll use the PSFs as is, but because in difference imaging, we want to have a continuous PSF over essentially the whole sky. We also will plan to use these PSF matched coads for measurements that don't include a PSF correction. So when you think about lots of the measurements we'll see later in the object table, you'll note that a lot of them don't include an intrinsic correction for the PSF. You get different answers if you apply the measurement to images with different PSFs. That includes aperture fluxes, it includes Cronin and Petrosian photometry, it includes those second moment shapes. All of those things need to be done on a PSF matched coed if you want to get consistent results across the sky and between different bands. The big downside of this is that it adds considerable correlated noise. You're convolving all those images with an additional kernel, and that does two things. It moves some power. It broadens the PSF, which is a problem not because you've convolved by some kernel you don't know. Convolved by a kernel you do know, but it moves some of the power in the image out to where there's more background noise, so that the signal of objects decreases, and it adds considerable correlated noise, and that's a bit of a pain for our pipelines to deal with. There might be different flavors of PSF matched codes. You can imagine that when you build them, you have to make a decision about which images you don't include because you have to essentially convolve to the worst PSF. And only the PSF matched coads that we use as templates for difference imaging are retained.
Hey, Jim, can I make one quick comment?
Sure.
So back to the direct thing, it's a bit of a not quite true statement to say it's mathematically the same as a longer exposure in the direct version, because it's rarely the case during a single exposure that the seeing has some completely discontinuous change, right? Mm-hmm. And you're going to get this funny superposition of good and bad PSFs. So just a little bit taking issue with point number 2 there.
Yeah, I think that's fair. It's the same in how it treats the noise in the PSFs, but it's very different in terms of the actual PSFs that you're using.
So can I ask a question about the match PSF? As you've described it, you're matching within a single band. In this context, there's no attempt to match PSFs from one band to another. Is that correct?
I think we will certainly match PSFs from one band to another. We may also do matching just within one band. But I think for a lot of the properties of these that we care about, we need to have not just one PSF within a band everywhere in the sky. We need to have one PSF in all bands everywhere across the sky. That's certainly true, for instance, if you want to use aperture fluxes to estimate colors. Alrighty, moving on. So deep is the kind of coads you'll see mentioned in many LSST documents, deep and best seeing. These are a form of direct coads in which we include data from almost every epoch. Essentially all but the very worst seeing epochs will go into deep coads. Whatever we can add that just essentially increases the depth of the image. Best seeing coads will be direct coads that only include data from the best seeing epoch. So this might only be 25% of the data. We don't really know where we draw the line because we don't really know what the seeing distribution is yet. And I think even if we probably could get good estimates of the seeing distribution, but we haven't done the experiments to see really what happens to different science cases when we put that cutoff in different places. Short period coads are direct or maybe detection coads in which the epochs that contribute only come from a particular date range. So we might make yearly coads, for instance, to detect slowly moving faint point sources, stars that have moderate proper motions that if we added them up across the whole survey, they would get smeared out. If we just looked in single epoch images, they might not appear at all. But if we make a short period coad, they should pop up. Optimal coads. This is not something that's part of the current baseline, but it's something we're thinking about quite a bit. There are algorithms that make truly optimal coads. You don't have to make a trade-off between optimizing the seeing and optimizing the depth. They're a lot trickier to implement, and they're in particular a lot trickier to deal with missing pixels. But I think we have some ideas on how to do that. And if we can pull this off, that would end up replacing both the deep and the best seeing coads, because there essentially would be no more trade-off to make between them. Well, I guess before I go on, any other questions about coads?
Yeah, this is Tom. I think I don't understand exactly what the warps are. So for you to be able to do the direct coads things, the pixels would have to be aligned somehow. So you're somehow mapping to some kind of shared pixel space. Over that.
Yeah, let's jump back to this diagram. So the idea here is that you start with your PVIs, and the first thing you do is you resample them. And what we call those resampled images are warps.
Got it.
Yeah. So this is because we have well-sampled data. We should be able to use some truncated version of sync interpolation with very good results, probably Longshos. And that interpolation problem just isn't a problem for us the way it is in, say, undersampled space data. All right. DIA data products. So this is difference images. That's just the science image minus the template. The template is a coad, but it's a coad that we've warped, PSF matched, and DCR corrected to meet the properties of the science image. We're trying the difference images. We want to essentially do damage to the coad, but not do damage to the science image, and that's because we expect the coad to have much lower noise than the new science image we're looking at. And therefore, any correlated noise we have will be much smaller. We do have some ideas in mind for how to deal with that correlated noise. We also have some ideas in mind for how to make sure that you can warp, or that you can PSF match, to a template, even though you want a PSF match by convolving a smaller PSF to a larger PSF. But there are games you can play with regard to how you detect objects, which also involves a convolution that can let you essentially convolve from the coad, even if it has a large PSF, to match the template, even if the template's original PSF is smaller, because what you care about is actually convolving both to form an optimal detection image. And I'm happy to talk about that some other time, but probably not for this presentation. DS sources are the detections and measurements that come from those difference images. These should require minimal deblending. And the deblending that we do have to do on them should be very easy. So as compared to our regular images, nearly all the DIA detections will be point sources. There are very few kinds of variable or transient objects that are not point sources to good approximation. They certainly exist, but their numbers are so small compared to everything else that for deblending purposes, it should be safe to treat things as point sources. The case in which that you have, a whole cluster of comets that are blended together is pretty small. It's also, of course, most important that the static sky will have been removed. So even if you have a crowded stellar field, in the difference imaging, you should have transferred that crowded problem into an uncrowded problem. In essentially the community that does this kind of difference image analysis, there's a big industry of removing false positives with machine learning classifiers, so-called real bogus. We were really trying to remove those false positives with better image processing, and we have some very good ideas for doing that. But we are certainly keeping the idea of doing machine learning classification in our back pocket if necessary. And if we do apply that, I think we haven't fully decided whether the DS sources will just disappear once we've decided they're bogus, or whether we'll flag them as possibly bogus. It depends on how confident we can be that they're bogus, obviously. Given those,
sorry, would the application of machine learning affect the timeline at which alerts can be released?
I don't think so. Those kinds of things, once you've training them is potentially slow, but applying them once you've trained them is fast compared to the other operations we have to do.
Right. Thank you.
So given those, the way blending interacts with difference imaging, LSST's official mandate on processing crowded stellar fields is that these DIA data products are the only ones that we guarantee to be high quality in crowded stellar fields. We have a best effort mandate for, or best effort non-mandate for doing other parts of the processing crowded stellar fields. And I think I've given another talk to essentially the same group of people last year on this topic. But we do guarantee that we're going to do well in DIA data products in the crowded stellar fields. All right, going back to the overview, we're now going to dive into the COAD processing steps. So this isn't all processing COADs. Some of this stuff is just log space operations, and that's what we'll start with here. So I'm not sure if you can see my mouse, but we'll start up in the upper left corner. We start with DIA sources, and we associate those together. This is just a moderately straightforward spatial match. And anyway, spatial match is never that straightforward, but it's not that hard either. That forms what I'm going to call preliminary DIA objects. And in the meantime, we're also going to take those detection coads, we're going to detect on them, and we'll come up with what we call footprints. And together, we'll take those coad detections and the preliminary DIA objects and associate those. And what comes out of that are initial objects, in other words, the things that will turn into objects, but we just haven't measured them yet, and DIA objects, which are essentially objects that came from DIA sources and then can be directly associated with DIA sources. Now, it's not obvious in this flowchart, but the DIA objects are actually a subset of the objects. So with those other objects, and which actually includes the DIA objects, we'll deblend those on the coad. Those produce deblender outputs that we call heavy footprints. And then we'll measure on the coad, and then we'll measure both on the direct coads and on the matched coads. And that produces more preliminary objects that have some of the measurements of objects, but not all of them. So let's take a moment then just to talk a little bit about what different kinds of objects are and how they're related. So DIA objects, as I just said, are defined by associating DIA sources spatially. Objects are defined by combining DIA objects and the detections from coads. And this is helpful because it can help resolve the ambiguities in the original DIA source association. If you have two things there sometimes and one thing there at other times, it can be difficult to say what's going on. But if you have a deep image, that can actually really help to clarify there. And I'm sure we can all come with lots of examples, whether it's supernovae on top of galaxies or quasars on top of galaxies or strong lensing, in which having more information really helps you resolve what's going on. What this means is the set of DIA objects for DRP is a strict subset of the set of objects. These rules are going to change when we get to the nightly or alert or prompt processing, so I'll be sure to call it out there too. It's important to note here that sources are not used to define objects at all. They are associated with objects after the objects are defined, and that matching is always going to be somewhat ambiguous. If you think about it, in some epochs, we could call a pair of objects one object. In other epochs, we'll call that one object. In another epoch, we'll call it three objects. And we will have measured those, three sources, two sources, one source. And regardless of which one of those we go with when we do the coad association step and define objects, it's always going to disagree fundamentally with what happened to one of those epochs, or more of them in general. So we can say what sources are kind of associated with an object, but it's really not anything more sophisticated than us doing a spatial cross-match for you. And that's useful when you're doing some diagnostic work, especially if you can limit it down to just the objects and sources that do have unambiguous associations, but it's not something you can expect to work for the full catalog.
So
what kinds of
question? In terms of querying that information, if I have let me get it right, a source that triggers an alert, then can I query the object from LSST?
If it triggered an alert,
query spatially.
Right. If you query, if it triggered an alert, then it would have been a DIA source, not a regular source, and those will be associated rigorously into the DIA objects, and therefore you can query which object that's associated with. With the comment that those are the ones produced in the nightly processing, and they're actually completely independent of the ones that are produced in data release processing. So we're essentially going to redo everything that happens in the nightly processing in the data release processing. So those will not be the same sets of sources and objects anymore. But when you get an alert, you will know what DIA source it came from, and you'll know what nightly DIA object it's associated with.
Thank you.
COAD measurements. So this is broadly the same kinds of measurements we did on the sources with a few more added in. We're going to measure centroids. We're going to measure adaptive moment shapes. We'll do aperture photometry. We'll do Cronin Petrosian photometry, which are specially scaled apertures for galaxy profiles. And then we'll measure what we call standard colors. And we're being intentionally vague about how you measure standard colors because this is a bit of a hard problem. It's easy to do if you're willing to degrade your images all to the same scene and do this on the PSF matched coads. We have some hopes of being able to do this with higher signal noise by fitting models, PSF convolved models to different epochs. But the main point here is that we're guaranteeing that we will produce a color measurement that is guaranteed to be consistent across bands. And that means that it may not correspond to the color of the full object, but it will correspond to the color of some well-defined or some stellar population that actually exists in the galaxy, rather than measuring one group of stars in one band and a different group of stars in another band. And all of these can be performed, or many of these can be performed on every band independently. So some of them you want to perform consistently across all bands. And I've tried to notate that here. I won't step through all the possibilities here, but you're welcome if you're to look in detail about exactly when and how we'll measure these things on the different kinds of codes. Any questions about those? All right, jumping back to the big overview page, the next step we'll jump into is this multi-epoch object characterization, which you've probably also referred to as multi-fit. The idea here is that we take those preliminary objects with some of their measurements, and we take the PVIs, and we go and fit models to all of the PVIs simultaneously for every object. All the PVIs that overlap a particular object simultaneously. And that completes our measurements of the objects. We then take those objects and go back to all those same PVIs, as well as all the difference images, and we do force photometry. And that produces force sources. And those will be our best measurements of light curves. It's, basically we're measuring photometry at fixed positions, consistent positions for every epoch. So those multi-epoch object measurements, there's two of them that we've called out. The first one is a moving point source, and this just means we're going to fit a PSF to all epochs with parameters for absolute position, proper motion, parallax, and constant per band flux. So as long as you don't have a super variable moving object, which obviously this can fit, but it won't fit perfectly, this should be the best stellar astrometry measurements we produce. And that's why people who are interested in stellar astrometry should be more interested in the object table than they are in the source table, even though you could also do stellar astrometry by matching up all the sources associated with a particular object and fitting proper motion and parallax to those positions. We're also going to do what we call restricted bulge and disk model. This is not a full bulge disk decomposition, but the idea is that we fit a PSF convolved linear combination of two galaxy profiles, an exponential profile and a Debocq alert profile. But those components will have the same ellipticity and center, which those of you who know something about galaxies know that the bulges don't typically have the same ellipticity as disks, but we also don't typically have enough information to constrain a different ellipticity. And as you'll see later, we're not quite sure this is what we use in the end, but this is a model that's been used successfully by some other surveys, particularly the CFH-TLS, and it's sort of a good default for now. And we plan to fit these independently in every band. Force photometry. So our plan is to measure aperture-corrected PSF photometry. So that's fitting with point spread function models for all objects on both PVIs and difference images. And the reason we're doing it on both PVIs and difference images is because while the difference images should be less affected by blending, the PVIs should have less noise. And the PVIs are particularly hard, actually, because when you think about it, we cannot really blend on the PVIs when we're doing force photometry, right? Many of these objects will have fluxes consistent with zero. We're only detected when we combine them, when we co-add and detected objects in the co-add. But we still have to somehow deblend them from their neighbors. And our vague plan right now is that we'll have to project the deblending results from the coads somehow to the measurement image. That means changing it to the appropriate PSF, changing the coordinate system appropriately, and then allowing the actual fluxes of the neighbors and the primary object to vary, or at least allowing the relative flux of the primary object we're force photometering to vary relative to its neighbors. So all of this is what's in the DPDD. I'll tell you what the DPDD is later if you don't know already, although I'm sure most of you do. But I want to take a moment now to talk about some things that are not super solid in the DPDD. Slight changes and maybe even larger changes that I think could happen between now and the end of construction. So first off, in those bulge disk models, I think we want to try to fit a single model to all the bands simultaneously. That may be in addition to the per band fits, or we might parameterize our per band differences in the joint fit. So we might say, well, we're going to fit all these models at the same time, but we'll allow the sizes to vary slightly in every band. Since the DPDD was originally written, the dark energy survey has been fitting models to data from all the bands simultaneously and has been quite happy with the results. So I don't see a good reason for us to not follow their lead there. I'd also like to try to tweak the parameterization. As I mentioned, bulges really don't have the same elasticity as disks, and we'd like to relax that constraint. The problem is coming up with a parameterization that does relax that constraint without adding too many degrees of freedom. I think it's already quite difficult to fit the degrees of freedom we've already defined there. In fact, the reason we're not fitting such profiles with flexible surface indices is because it's much more stable to fit two profiles with fixed surface indices because it's a linear combination rather than how that highly nonlinear surface index parameter. So I think this is a topic of active research, and we're not quite sure how we'll solve it yet. For those of you who care about recleansing, I should add that we'll probably run a modern non-parametric shear estimation algorithm like BFD, the Bayesian Fourier domain, or meta-calibration as well, instead of relying on the bulge disk fits for shear measurements. Back when LSST was going through its final design reviews, the state-of-the-art shear measurement codes were all forward modeling Bayesian methods, which is more or less like our bulge disk model. But since then, I think the field has really been taken over by non-parametric methods, and those are actually much cheaper to run. And I don't see any world in which we wouldn't do that. It's just a matter of waiting to see what the right one is at the time we hit operations. None of them are terribly hard to implement, and we certainly expect the stage 3 surveys to continue to do a good job of implementing them. And we can either take their code or re-implement their algorithms when the time comes. Some less likely, but I think still not improbable changes. I mentioned optimal coads, and we've been talking recently about doing per object optimal coads. This avoids a lot of the problems of missing pixels if you can just define, okay, for this object, I only want the epochs that don't have any missing pixels. That's a much safer set than I want for this large area of the sky. I want only the epochs that don't have any missing pixels. That would remove all of your epochs. So if we can get that working, I think it's actually possible that we could drop the multi-epoch object characterization entirely. And this would obviously be a big change request that lots of people would have to approve. But I think we could, instead of doing the moving point source holes on all of the epochs, we could constrain them from a combination of those short period coads and per epoch centroid derivatives measured in force photometry. So what that means is we would sort of get a decent model from the per epoch coads of where the star would be on every epoch. And then when we do force photometry, we would do force photometry at those positions, and we'd also compute derivatives with respect to the centroid without actually letting the centroid vary. And that gives you some more information that you could use to constrain an even better model of the stellar proper motion and parallax. The bulge disk models are quite a bit easier because the only reason we were planning to do those in multi-epoch mode before was because we weren't certain that we could make a truly optimal coed. And I think that wouldn't lose any information and wouldn't introduce any systematics. I think we're pretty close to convincing ourselves that we can do that. And if we can convince ourselves that doing that is actually easier than doing the full up multi-epoch fitting, we'll propose that we measure the bulge disk models on those per object optimal coeds. There are a few data products that I have not really called out here. In the first two cases, it's because they're, well, at least from our perspective, rather simple, and that's variability characterization. So if you look at the light curves that are derived from the force photometry, you can do some standard statistics on that and come up with a few numbers that characterize the variability that's very useful for searching on. Generally, we expect science users to do their own analysis of light curves, but some characterization that they can filter on is, of course, very useful. Photometric redshifts are things that you can derive from the colors. They're not image processing. I think we largely expect the community to do a better job of photometric redshifts than we will probably do internally, unless we just take what the community is doing best and re-implement it or take in their code and run it. I think the details of how we will do that is still a little bit unclear, but because it's nothing else we do depends on those photometric redshifts, it's something that we can kind of defer to the end of the processing, and that makes it very easy for us to use code and algorithms from the community. One thing that we do need to do a better job of defining soon, and that we're working on, is data products that describe the survey geometry, masks, completeness information. I think it's almost certain that we'll do this via some hierarchical pixelization of the sky. There's a VO standard to use HealPix for this. There's also a lot of tradition in code for doing this with HTM, and of course there are some more exotic ones that might perform better. I think if we can convince ourselves that the HealPix mock approach is not clearly worse in some way in terms of geometry or computational efficiency, then we'll probably go with that because it is sort of a developing standard. But I think we're not completely sold on that idea yet. I think no matter what we choose, we're going to ensure that our software tools that you can use to work with these data products, either because we adopt something like HealPix and mock that does have existing tools, or because we develop them ourselves. I suspect we'll develop some ourselves regardless, although we may rely more on the community if we go with HealPix. All right, that's it for data release processing. I'm about to switch to prompt processing. Do we want to have any questions about data release processing first?
I had a real quick one, Jim. So
Sure.
You said force photometry to do variability characterization. Is that force photometry on the difference images or on the visit images, PVIs?
That's a good question. I think it would not be too hard for us to do variability characterization on both, although I think that would probably end up being quite redundant. And I could imagine us doing it on both, doing some tests and figuring out, well, for the objects for which these variability classifiers are most useful, these ones, the ones from PVIs or the ones from difference images tend to produce the best results, and we'll just go with that. I think that's a good question. We should make sure that doesn't get lost, though, because I think when we essentially upscoped a little while ago to do force photometry on both because it was easier than trying to decide in advance which one we would choose, we did not think about what the impacts would be on which one we'd use for variability.
Jim, quick question. Could you go back to slide 21? This is on stack fit, multi-fit. So there you look at individual images. I think this is the correct slide. You look at individual images and try to do this fit. But each image, of course, has its own particular point spread function, which is going to be different for each. And you want to use the point spread function map that you get from that image, correct? In doing this?
Correct, yes. So in all of these cases, we will be taking some common, assuming we do this in multi-epoch theme mode, we will take some common model, convolve it by the different PSFs of every exposure, convert coordinate systems to the coordinate system of every exposure, scale by the photometric calibration of every exposure, and then compare to the data.
Right. Thank you.
All right, any other questions on DRP? All right, so prompt processing. So I'm going to highlight here what the big differences are. There's no object table, no coad images. There's actually no source table either. I forgot to mention that. And it uses the coads and the reference catalog from the last data release as inputs instead of producing them itself. And the result is much simpler pipelines. There's no iterative refinement or self-calibration steps of the sort we saw in the DRP. And I think that of this as having three major pieces. There's the part where we produce transient alerts within 60 seconds of the exposure. This is the part that's most well known. It's where most of the image processing happens. After that, there are some catalog processing steps and some image processing steps that can be stretched out, over the next 24 hours. And that includes refreshing the solar system object catalog. This is what we call MOPS, and performing force photometry on new and existing DI objects. Now, I should also emphasize that all of the data products I'm talking about in prompt processing are distinct from the ones that are in the data release processing. They are new versions of what are conceptually at least similar things. They're produced differently, and they essentially do not refer to each other except for the fact that the prompt pipelines will use the COAD images as templates from the last data release. All right, so here's the familiar, well, maybe slightly familiar now, diagram of the data release processing. And I'm just going to flip this to the prompt processing. And at first glance, it looks pretty similar. I've tried to keep things in mostly the same places when they're similar. But you can see now that instead of doing the co-addition and difference imaging, we're just doing difference imaging. We're not producing those sources. Instead of doing COAD processing, we're just doing association, and that includes MOPS. We're doing some alert distribution as well. Instead of multi-epoch processing, it's just force photometry. And the COADs are now inputs instead of being outputs. So this is zooming in again. So we're going to zoom in now on the image characterization step again. This is the one we saw before. And this is the version in the nightly processing. As you can see, it's much, much simpler. All we're doing is we're taking those raw images, calibration images, reference catalogs. We're doing single visit processing, and we're producing PVIs. All those extra steps involving cal and the later refinement of that single epoch processing have gone away. And that's what allows us to get this done in 60 seconds, one image at a time. Similarly, this is the big complex diagram for co-addition and difference imaging in DRP. The version of this for AP is much simpler. We essentially take those matched COADs that we had from DRP, we difference them against the PVIs that are coming out of the nightly processing, we produce difference images, we process those, and we get DS sources. And that gives you an idea of, I'm not going to walk through all the other pipelines in a similar way because they start to have less in common, even less in common than these ones. But that gives you an idea of how both pipelines are producing data sets that are named the same thing, but they really are not quite the same thing. We're either taking outputs from DRP to use in the alert processing, as with those COADs, or we're simply not doing refinement steps that we do in DRP, as with this missing joint cal and image characterization. And that doesn't mean that the things in alert production are necessarily worse. Essentially, in data release processing, we're starting with nothing, and we're forcing the survey to calibrate itself. But in alert processing, we're able to use the calibrations from the last data release directly. And so the new images aren't contributing to that calibration, but they're also getting those good calibrations. All right, so what are the data products that are coming out of the prompt processing? So we've got the PVIs. These are very similar to the data release PVIs, but they have less sophisticated image characterizations. And in particular, that means less sophisticated PSF models. In data release processing, we need to do very high fidelity PSF models that can be used for weak lensing. They're going to have to be spatially and wavelength dependent. The ones that we use for data release processing really only need to be good enough to do very simple calibrations to match into Centroid and then essentially match to the data release calibrations. The difference images in DS sources are even more similar to the things we produce in the data release. The data release versions might be able to do a slightly better job of masking some kinds of artifacts. We'll have, again, more iterative steps there, and they might have less noise in the templates at the start of the survey. If you think about it, when we start the survey, we'll have to get templates from somewhere, but we won't have that many compared to the new epoch. Whereas when we have a data release, we'll be able to make, we'll be able to use all the data we have at that point to make the template. And that may produce better results in data release at the beginning of the survey. By the end of the survey, that won't matter. So I don't think there's really much downside to using the difference images and DS sources from the alert processing. The DIA objects are also different. In the prompt sections, these are created directly from associations of dia sources. There's no objects, there's no coad detections, so all we can do that spatial association. And that means they won't benefit from that refinement with the coad detections that you can do in the data release. The force photometry in the prompt processing is only done on difference images using dia object positions. We're not going to do the force photometry on the PBIs. As I said, that involves projecting complicated deblending results from the coad down, and we don't want to do that in the prompt processing. We also, of course, can only use the dia object positions because we don't have objects in prompt. Solar system objects I really haven't talked about yet. I sort of glossed over the fact that they are included in the data release processing. They are. And the differences here is actually that not only are the ones in the nightly processing created incrementally by linking up those dia sources, they're also in the nightly processing going to be able to use other sources like the MPC. And the data release version, in contrast, is going to only use LSST inputs. And what that means is that actually in this case, the incremental nightly one is probably going to be a better, at being our best estimate of what's going on in the solar system. But the data release one has the advantage that you can do a much better job of characterizing your completeness and your selection functions because it uses only LSST data that we understand much better. The one thing that the data release processing has absolutely nothing to do with that happens in the prompt processing is, of course, the alerts. And this is a packet of information about every dia source that we detected, and that includes its relationships to known dia objects and known SS objects. And unlike actually everything else here, that's also going to be essentially completely world public, not just available to access holders, I think, primarily because it's restricted. Alrighty, so that's actually all I had for the prepared presentation. There's plenty more information out there. I would certainly recommend starting with the data products definition document. We call this the DPDD. There's a link there. This is concise. It focuses on the data products. It's also polished, but it still uses that confusing level N nomenclature. I mean, we've got actions open to fix that, but it hasn't been done yet. So if you do read through that, just sort of take a step back and think about this presentation, I think, gives you a better set of labels to use, even though there's much more detail in the DPDD. The other thing I'd say is that the DPDD is very focused on what the actual baseline is. It's the things that we have said that we will do and won't decide not to do unless we go through a big change it. I've talked a bit more here about things that we might change, and that's especially true in this document, the Science Pipelines Design Document, LDM 151. This is much more detailed. It focuses on the algorithms rather than the data products. It's both, I think, a bit rougher. It was written by many authors, and hasn't gone through that many iterations. It's also a bit more speculative. In cases where we're not sure what algorithm we'll use, this document is not afraid to speculate about what algorithms we might use, rather than sort of picking the best one or the one that is our best guess at the best now. If we're not sure, this document tries to capture where we're not sure. There's a special piece of the community.lsst.org site that is where we encourage you to ask questions about the data products. There's a link to it right here. Several of us, including myself, monitor that for questions, and we make sure we provide good answers. And of course, there's a whole set of 5 more future talks on the details of this. And that's about it. Thanks.
Thank you, Jim. This was fantastic timing and great talk. I certainly am going to need to review the slides a few times to absorb it because it was a lot of stuff. I've lost the connection through BlueJeans on my computer, so I don't know if there were any questions that were not asked on the chat. I don't see the chat right now. Is there anything left?
I will pull that up and take a look.
Yeah, I just wanted a little bit of clarification. So I'm trying to understand the light curves coming out with the alerts. So is the entire light curve recomputed every time a prompt dire object is imaged?
So I think, well, what I would refer to as the light curve is actually just the set of forced photometry measurements. And so when there's a new science image where an existing dia object exists, we will do force photometry there. And that will add another data point to the curve. And I believe that we will also then update the variability measurements that are derived from that light curve.
Okay. But you wouldn't
But
go
you will
back.
not.
Yeah. Sorry.
Go ahead, Michael.
But you wouldn't go back and redo the force photometry at the slightly different dia object position once it's had a new dia source added to it.
That's correct.
Okay. And then the other quick clarification was, did I understand that the alert light curves, or the light curves associated with alerts, will only extend back to the beginning of the current season? You wouldn't include in the alert package the whole light curve from the beginning of the survey?
So first off, I would say remember this question and ask Eric Bellum during his presentation. My recollection is that there's actually a 30-day rolling window.
Oh, okay.
And that we include the 30-day rolling window in the alert.
Okay. Thanks.
Excellent. Are there any other questions? Not brilliant. So there's a link to the live menu that we were collecting during the talk. It's in the chat. I will post the link on Slack as well. Then that will be posted on community, on the community board that we created to discuss these talks in more details as well, and the video hopefully worked out well. I didn't have any control over that, so hopefully we'll have a good video of this talk to be posted on the scientists webpage on LSST as well. And stay tuned for the day of the next talk, which will be, I forgot already, but Jimmy was in your second slide, so I'll pull that out, which will be on the photometric data products, and it's penciled in for February 27th, and it will be Robert Lupton. Okay? Thanks, everybody.
Thank you.
Thank you, Jim. Very helpful.
Bye. Thanks, Jim. Thank you so much.
Bye.
Thanks again, Jim. Bye-bye.